The quiz on Friday will look like what you see here. I am going to give you a fractional function. I will give you the first derivative and I will give you the second derivative. If it is super ugly, as far as really not factorable real well, like this one, I will tell you where the non-factorable or the weird piece equals 0. So I will give you the zeros so that you don't have to guess. Okay, so kind of like the way this is set up. Okay, so let's go through the process of the 11 steps that you see here. And this is exactly the same order that I'll expect to see it on the quiz, okay? So where does the function have holes? So the first thing you want to do for question number 1 is you want to take the first derivative and you want to put it into factored form. So the top is x plus 1, x minus 1. We can factor out an x, and then we can factor it one more time, and you get x minus 2 and x plus 1. Okay, so, however you got to do it, please factor that as far as you can. Next, the holes occur where any factors in the top and factors in the bottom are an exact match. So this is where x plus 1 equals 0, or at negative 1. So I'm going to put a little placeholder there because it's a point where we have a hole. So we'll fill that in a little bit later. Okay. Vertical asymptotes also can come from that factored form. But let's take and cross those things out that I said were exact matches. And let's use this version to find our vertical asymptotes. So it is where our bottom that is remaining, the factors that are remaining in our denominator, equals 0. So this would be at 0 and at 2. Okay. So we have vertical asymptotes at x equals 0 and x equals 2. So 1 and 2 are found from the original function in factored form. So that's why you want to think about that. Okay. Also, step 3 will be from that factored form. 1 and 2 give you the answer of 3. So I'm going to write the domain. I have to skip negative 1, 0, and 2. So just think about the number line, go in order until you skip those values. So we're going to go from negative infinity until we get to negative 1. There's a hole there. Then we're going to get up to 0. There's a vertical asymptote there. Then we're going to get up to 2, and then there's a vertical asymptote there. So you'll notice that I have 3 gaps, 1 for the hole, 2 for the vertical asymptotes. So you need to have a graph that is in 4 pieces. The ones that connect through the hole, it's kind of going to be like this piece, and this piece. So it's kind of 3 distinct pieces of our graph. This just has a little hole in there. Okay, so 1, 2, and 3, all related, kind of do it together. Now let's take a look at our x-intercepts. Our x-intercepts are also related to our original function. Just take the top and set it equal to 0. So that's x minus 1 equals 0. We only need the factor that remains. So that's going to be at 1. Now that's a point. So that is the point 1, 0. The y-intercept is from our the original function. You just get to plug in 0. Now you can plug it into the top or into the bottom. It doesn't matter, the original or the reduced version. But we do get negative 1 over 0, which is undefined. So there is none when that happens. Now the reason it became like that is just this factor right here, that plain old x. We never hit the x-axis, and we have a vertical asymptote there. So all those pieces should line up. Okay. Horizontal asymptote or slant asymptote. We have the higher power in the bottom. So since the bottom is a higher degree, it's always equal to 0. So you'll notice I haven't touched the derivatives yet until I get to problem number 7. So 7 and 8 are going to use our first derivative. Now, our first derivative is almost in factored form. If it's a quadratic, you may have to use a quadratic formula it's up on the board. You may need to use a quadratic formula, hint, hint, to figure out what the zeros are. So the critical points occur where the first derivative either equals 0 or is undefined. If those undefined points also work in the first derivative. There are undefined points at 0 and 2, but those aren't critical points. They're just undefined points. We have nothing at 0. We have nothing at 2. They are vertical asymptotes there. So they're not really considered critical points. If you put them down as 0 and 2 being critical points, it's not a big deal, but it's not technically, it's not a point. It's an asymptote there. So the critical points occur where x squared minus 2x plus 2 equals 0. So that is solvable with the quadratic formula. Now remember, your quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. So that is a formula that never goes away from the time you're in Algebra 1. So let's go ahead and do that. Now, if you get i's, that means there are no critical points. This function just doesn't have any maxes or mins. But anyway, so we get negative b plus or minus the square root of b squared minus 4 times a times c is negative 8. As soon as we got to that point, this right here says, because it's an I technically, there are none of these. Now, if you get a number, like if we would have got 2 plus or minus the square root of 7, that's okay, but we can't have negative 7 or we can't have negative 4. That isn't a point, okay? But we will have either an increasing or decreasing spot. We still make the plus or minus chart, skip our vertical asymptotes. The whole, you don't really have to skip too much because we're going to use our second derivative, or our first derivative should be okay. So let's just plug in test values. Let's plug in negative 1, 1, and 3. Now I'm going to plug it into the entire thing. Well, I guess I can only have to plug it into the top. Now, why do I need to only plug it into the top? What do we know about the values of things that are squared? They're always positive. So the x squared is always positive. The x minus 2 squared is always positive. It doesn't do anything, okay? So we have technically positives because of the bottom. We have all negatives because of that. So now we just got to plug into the x squared minus 2x plus 2. Okay, if we plug in negative 1, let me put my test values down here so they look nicer. You can read it a little better. Okay, so if we plug in negative 1, only thing I'm checking really is this lovely thing. If I plug in negative 1, I get 1 plus 2 plus 2. That's a positive. If I plug in positive 1, I get 1 minus 2 plus 2, which is a positive. If I plug in 3, I get 9 minus 6 plus 2, which is also a positive. Okay. So now let's look what's happening. This is negative, this is negative, this is negative. So what's happening is it is decreasing everywhere. It is decreasing because it's negative, from negative infinity until our first asymptote, from 0 to 2 in the middle of the asymptotes, and then from 2 to infinity. So it's decreasing everywhere. It was negative everywhere. And that happens sometimes because we don't have a real critical point. There's no local mins and maxes. And I didn't put that on there. I don't know why, I'm so sorry, but there's no maxes or mins. I don't know if I've asked that of you, but you're going to have to know that when it comes to time to graph it. So now we're talking about 9 and 10, which is to our second derivative, okay? So I have told you the 0 in the top. The only 0 is when x equals 1. Remember, 0 and 2 still don't work because they don't work in the original, the first, or the second derivative. So we have to find, is 1 an inflection point? Okay. Let me take a picture of that. Okay. So we've got that second derivative there. I told you that there was a possible inflection point at 1. Now, that's a point. So let's color that one in to remind us, hey, that might be an inflection point. These are not points. Those are asymptotes. So put open circles there just to remind you that there's a something messed up in the graph right there. Okay. Now, what are my pieces? Now, I'm going to label all of them, okay? So I need to put on the 2. Don't forget, put on everything. I'm gonna say that x cubed thing. So I'm going to be lazy. And then I just have a plain x cubed, and then I have an x minus 2 cubed. So that's all the factors that I see. My graph is so straight and beautiful. Let's plug in some test values. -1, 1/2, 1.5, and 3. These are great, aren't they? Okay, so if I plug in -1 to 2, no matter what, that's always positive. So I can just put some pluses there. Now, let's take care of this big, giant, disgusting x cubed, that thing right there. Okay. So if I plug in -1, let me tell you what I get. I get -14. That's a definite negative. If I plug in 1/2, I get a negative again. If I plug in 1.5, I get a positive. If I plug in 3, I get a positive. Okay, now let's do x cubed. If you cube a negative, it's gonna stay negative. If you cubed positives, it's gonna stay a positive. So that looks like that. Okay, now let's do the final quantity, x minus 2 cubed. If you plug in -1, you get -3. If you cube a negative, it's going to stay negative. If you plug in 1/2, you get -1.5. When you cube that, it's going to stay negative. 1.5 minus 2 is also negative, but when you cube it, it's going to stay negative. And then 3 minus 2 is finally our positive. When we cube it, it's going to stay a positive. Okay. Anyway, so now let's think about when we have these things multiplied or divided together. 3 negatives become a negative. 2 negatives become a positive. 1 negative stays negative. 3 positives stay positive. So where is an inflection point? There's an inflection point when x equals 1. That's the only place where we have a change in concavity for a point that actually works. It's the only time that happens. So let's go back up here And on number 10, let's say that our inflection point is at x equals 1. Or we could even put 1 comma, and we can fill that in. Concave up, concave down. The positive sections are between 0 and 1, and from 2 to infinity. So those are our concave up sections. Our concave down sections are from negative infinity to 0. I'll zoom into this in a minute. And then from 1 to 2, thank you. Okay. And then 11 says to graph it accurately. So obviously there's nothing you got to put there. Okay. But we do need to finish off some point values. Now let's think about the points we haven't put on there. -1 and 1 for sure. Okay. Okay, so let's, when we go ahead and graph this graph, let's first put on the vertical asymptotes, okay? We'll let everybody get caught up. Okay, so let's make this one a -1 and 1. So I'm going to count every other space. Okay, so we have a vertical asymptote at 0 and 2. I usually put those on first. Okay. Now, -1 is a whole, but remember, let's write down, I'm going to write down here, that factored form, okay? The factored form is what we can use to determine what the heck's happening. So at -1, we get -2 over -1 times -3. So it's really -2 over 3, or -2/3. So at the point -1, -2/3 is about there. We have a whole. So let's finish our whole value as at -1, -2/3. Okay. If we plug in 1, we get 0 over -1, which is still 0. So at 1, we are at 0. Now remember, that is a point of inflection, so a change in concavity. So let's analyze. What I like to do when I'm graphing things like this is let's analyze in the middle of the asymptotes, then let's analyze on the sides of the asymptotes, okay? So let's think about what we learned about that section. We are decreasing the whole time. So if we went like that, would we be decreasing? No. So I'm thinking it's going to look something like that, right? Now let's check our concavity. Concave up, concave down. Does that work as well? Yes. So by using logic, now if logic fails you, feel free to plug in +1/2 and 1.5. You guys have calculators. Plug in the values. But technically, we know that the concavity should be my cup is up, my cup is down. This is an inflection point. It is decreasing the entire time. So all those things go together. Now, horizontal asymptote, the horizontal asymptote was at 0. So let's put that on here for the ends. So that's going to determine what's happening here. So we're either sandwiched in here or sandwiched in there. Same thing here. We're either here or we're here. So what are we? We already have a hole there. So that means that the graph has to connect to that hole. So technically, this one was a freebie. Now let's check. Is it doing what they said it was? Is it decreasing? Sure is. Is there a hole there? Yes. Is it concave down? Is my cup upside down? Yes. So all the things we know about that region have held true. Okay. Now this is the region I'm a little concerned about. It's got to be in that region, it's concave up. It still has to be decreasing. So I'm thinking there's my cup is up and it's going downhill, right? So I'm thinking that's where my piece is. Let's plug in a number. Let's plug in 3. Now I'm plugging it into the nicest version. It doesn't really matter, but it's helpful to always just keep focusing back on that reduced version. If you plug in 3 on the top, you get 2. On the bottom, you get 3 times 1, or 2/3. So my conclusion was right. I am up about right there. So to connect it, follow your asymptotes. My curvature has to be concave up. My cup is up. I am going downhill, downhill, downhill the whole time. So what you're getting for the earlier answers should reflect on your graph, or your earlier answers are wrong, or your graph is wrong. Okay. So on the quiz, I will give you the first, second, and third derivative, and then you are going to do the 11 steps that you see here. Yes. Yes, it's just one problem, 11 steps. It's going to take you the whole period, I would assume. Okay. So if you could please at this time turn this in, get yourself some points for the review. Please study, study, study. Try it again without me. The quiz is on Friday.